Yeah, it's a great honor for me to be here speaking to you all. As I already said to Jared and Angela before we started, one of the things about Zoom meetings is that it's hard to ask questions. So please use the chat facility if you want to, and maybe Angela can keep an eye on that a little bit and bring anything up, or just interrupt me. And also, if you see on the screen here my email address, I'm happy to get questions by email afterwards if you have any questions. So don't hesitate to contact me. And the other thing I wanted to say before we start is I've tried to make this really elementary, so some of you will already know nearly everything, maybe actually everything that I say, and I'm very sorry for you in that case. But you know, as you get old, like I am old, you try to make your seminars more and more accessible to everybody, because you get really fed up. I do anyway, sitting in seminars where I don't understand anything. So I try to go in the other direction to some extent. So apologies if it seems too simple for you, and never mind. Okay, let's go. So here's the plan, and this is pretty ambitious, and we may not do everything, but I'll try to get through most of that. So first of all, what is a Hopf algebra? So I'm going to make things a little bit easier for myself by assuming always that we've got a field that's algebraically closed and characteristic 0. So a Hopf algebra is simultaneously an algebra and a coalgebra, and we'll define those things separately and then bring them together. So first of all, what is an algebra? An algebra is just a ring, which is also a vector space over K, and the two structures interact by saying that the set of scalars, that's the set of the elements of the field times the identity element, should be in the center of the ring. So that's what an algebra is. And examples that we're all familiar with: polynomial ring in any number of variables over the field K, and the n by n matrices for any positive integer n over K. Those are K algebras. So one way we want to think about a K algebra when we're trying to define a Hopf algebra is to think of the multiplication in the algebra as a map from the ring R tensor itself, so R tensor R, into R. And the reason for doing that is because when we go to the kind of dual structure that makes up a Hopf algebra, which is called a coalgebra, we're going to reverse that map in a certain sense. And we're also going to kind of dualize the axioms. If you think about the axioms for a ring, there's an associativity axiom, and that becomes in the coalgebra side a co-associativity axiom. So here's the definition of a coalgebra. A coalgebra is just a vector space C over K with two linear maps. The first one is called the coproduct or the co-multiplication, and it's nearly always written by a capital delta, and it goes from C to C tensor C. So that's the reverse of the multiplication map in the algebra. And the co-unit, which is this map epsilon, is a linear map from C to the base field. And these have to satisfy some axioms. This first one is the dual of the associativity axiom, and it's called co-associativity. And it just says, if you look at what that equation is saying, it says that if I apply delta twice, in the two possible ways I can do that, because if I apply delta once, I get an element of C tensor C, and then I can either hit the first entry in C, first set of entries in C with delta, or the second set. And this axiom says it doesn't matter. I get the same answer every time. So that's the co-associativity requirement for delta. And the requirements for epsilon say if you apply delta to an element of your coalgebra, and then you hit in the first equation there in that pair, you hit the second argument in the tensorands with epsilon, so that gives you elements of k, then you just really get the original element back when you do that. And similarly, if you hit the first elements with epsilon, you get the original element back. So if you haven't seen those axioms before, especially the second and third ones, don't worry too much, because they'll sort of be obvious in the examples, and they're really just duals of the familiar axioms for a ring in a certain sense. And as I said already, delta is the co-product of the co-multiplication, epsilon is the co-unit. And then there's this notation, which goes back to this guy called Sweedler, who wrote the first book on the subject, which says we'll write delta of C as sigma C1 tensor C2. And the point about emphasizing that is we should remember that these C1s and C2 are not uniquely defined by the co-multiplication. There's lots of different ways of writing the same element of the tensor product. And so it's just a kind of formal way of recording what's happening without being too specific. So an example of a coalgebra, a very simple one, is if you take any vector space over K with basis B, then you can view it as a coalgebra with the co-multiplication just being defined by delta of V being V tensor V for any V in the basis, and epsilon of V being 1 for any for all the V in the V's in the basis, and then extend linearly in both cases to the whole of V. And we'll see that example of a coalgebra coming up shortly in the Hopf algebra. Hopf algebra that we're all familiar with, and you can maybe think of ahead before we get there. So a bialgebra, we're heading towards a Hopf algebra now. A bialgebra over K is just an algebra which is simultaneously a coalgebra. And of course, these two structures, they have to agree with each other. They have to harmonize. And the way we impose that harmony is just to say that the co-product delta and the co-unit epsilon should be algebra homomorphisms. So that's what a bialgebra is. So here's an easy example. Just take polynomials over K in one variable X and send any power, all the powers of X to X to the I to X to the I tensor X to the I, and all the powers of X by epsilon should go to 1, and then extend linearly to the whole thing. That gives you algebra homomorphisms. And if you think about it, go back and think about the axioms, you'll see very easily that they're all satisfied by that rule. So a Hopf algebra is just a bialgebra with an extra ingredient. And the extra ingredient is this thing called S in the definition there on the slide. And it's a map. It's a map from H to itself. And it's called the antipode. That definition came from the French in the 1950s. I'm not sure why, but anyway, that's what it's called. What is S? It's a linear map, first of all, and it satisfies these two conditions on the bottom of the slide. First of all, you have this condition that S applied to a product of two elements, H times T, should be S of T times S of H. Now, that looks wrong if you haven't seen it before. It looks like the right-hand side is in the wrong order, but actually it's correct. And S is what's called an anti-homomorphism. And it's meant to be, it should remind you of the rule for inverses in a group, you know, that the inverse of G times Y is Y inverse G inverse. It's basically coming from the same idea, I suppose. And then the second rule says if I take an element, any element H of my Hopf algebra, apply the co-multiplication to it. So that, remember, that gives me, by Swedler notation, H1 tensor H2, sigma H1 tensor H2. And then if I hit either the first arguments or the second arguments with the antipode and squash everything together and add up, then I just get epsilon. So the fancy way to say that, which some of you probably will know, I'm sure, is saying that the antipode is the inverse to the identity map when you apply the convolution multiplication to the set of linear maps from H to itself. So the antipode is the inverse to the identity map. That's what the second axiom is saying. And that should kind of give you the clue that the antipode is some kind of inverse. It's really kind of modeling the inverse in a group in some sense. Okay, so that's the definition, which, I mean, if you've seen it before, if you're familiar with it, everything up to now is kind of boring. If you're not familiar with it, I'm sure it looks terrible because, you know, why on earth would you have all these axioms and all these maps? It looks like you're going to get a very artificial set of objects. The amazing thing is that there's a huge prevalence of Hopf algebras across mathematics, as we've gradually realized over the last 80 years, I suppose, since Hopf first introduced them. And so I'm going to give you some examples. First of all, what's called co-commutative ones. I'll define co-commutative at the bottom of the slide. Let's start with the examples. First one, group algebras. So take any group and form its group algebra KG. So you'll remember that just means the vector space over K with the elements of G as a basis, and multiplication and extending the multiplication on the field and the multiplication on G. And that's a group algebra. We have to define the co-product and the co-unit and the antipode, and there they are. And you recognize this co-algebra structure here as being the one that I said you could apply just to any vector space. So here we're applying it to the vector space KG with the basis, the elements of the group. With the added ingredient here that we can define the antipode, and S of G is G inverse for G and G. And the other very important class of co-commutative Hopf algebras are enveloping algebras of Lie algebras. And so if you take any Lie algebra G over K, then form its enveloping algebra, which I'm not going to define, but you probably know already. It's an associative algebra whose representation theory is the same as the Lie representations of the Lie algebra. So it's a crucial gadget for doing Lie theory. So it's certainly an algebra by definition. Hopf algebra means we have to define a co-product and the co-unit and the antipode. So the co-product we define by setting it for the elements of the Lie algebra, say X. Delta of X should go to X tensor 1 plus 1 tensor X. The co-unit on the Lie algebra sends the Lie algebra elements to 0, and the antipode sends elements of the Lie algebra to their inverses. And just pause just to think for a minute, why is it enough for me just to define what these maps do on the Lie algebra, when after all I've got this infinite dimensional gadget, the enveloping algebra, actually sitting there? And the answer is because we said these maps have to be algebra homomorphisms in the case of delta and epsilon, and an algebra anti-homomorphism with this funny reverse row for the antipode. And so that means once I've said what what the maps do for a generating set for the algebra, that is the Lie algebra in the case of the enveloping algebras. Once I've said that, then that's it fixed. That's what the maps have to do for every element of the ring. So it's enough to say what happens for the generators. So as the top of the slide said, these guys, group algebras and enveloping algebras, are examples of co-commutative Hopf algebras. So you probably can guess, even if you haven't seen before, what co-commutative means. But there's the definition. It just says that the co-product is symmetric. If I take delta of H for any H in H, and then flip the tensorands, I don't change the answer. So it's kind of the dual of the algebra being commutative. So those are fundamental examples of Hopf algebras, and they're co-commutative ones. What about commutative? So this class is very important as well, but coming somehow from a different direction, coming from algebraic geometry rather than from Lie theory. So starting point is an affine algebraic group. So as you know, that's just an affine algebraic variety where the multiplication in the group and the taking of inverses in the group are morphisms of the variety. So for instance, you might take G to be the special linear group of n by n matrices with determinant 1 over k, or any finite group is an affine algebraic group over the field k. So G could be those things, for instance. So then we can consider, essentially by definition of G, we can consider all the polynomial maps from G to itself. So that's just the coordinate ring, which I'm writing as O of G for G, viewed as an algebraic variety. So it's by this affine condition, that just means that O of G is a finitely generated algebra, and it's a commutative algebra. So it's a factor ring of some polynomial ring in a finite number of variables over the field K. So first of all, why is it an algebra? It's an algebra just by essentially the multiplication in the field. So F times H, on the left-hand side of that display there, F times H, two polynomials in O of G applied to an element G of the group. The definition of F times H is just F times H of G is F of G times H of G. Then the co-unit just means evaluate F at 1. Co-unit of F is just F evaluated at the identity element of the group. And the antipode, S applied to an element of O of G, is the map from G to the field that sends the element G to F of G inverse. So what about the co-multiplication? So that's slightly more complicated, and what you have to take on trust or convince yourself is that if we take the tensor product of O of G with itself, that's the same as the coordinate ring of the direct product of G with itself. That's just O of G tensor G. And remember, for the co-product, what are we looking for? We're looking for a map from O of G to O of G tensor O of G. So that means if we take F in O of G, then delta F should be a map from G cross G to K. And all it is the map that sends a pair of elements, G1, G2, in G cross G2 to F of G1, G2. So if you haven't seen this before, it's worth just pausing and looking at it for a minute, because it's really a brilliant gadget, this O of G. It encodes the whole structure of G in the structure of O of G as a Hopf algebra. Because you see the the co-unit, epsilon up there, that encodes the identity element. The antipode is encoding taking inverses, and the co-multiplication in O of G is encoding the multiplication in the group. So we've got all the information in G is encoded in the Hopf algebra O of G, and vice versa, of course. So wonderful thing, this affine algebraic group. And so this is a Hopf algebra, and it's commutative, obviously, from the the definition of the multiplication. You can see that up there. Let me show you what it looks like for SL2, maybe the easiest non-trivial example. So polynomial maps from 2 by 2 matrices. That means we can generate them by the 4 coordinate maps. So x11 there is the map that takes a matrix, a 2 by 2 matrix, and shoots out its 1-1 entry, and etc. for the other ones. But we want to say that we're only taking maps from matrices whose determinant is 1, because we're looking at SL2. So that means that we should be sending the determinant to 1, so the determinant minus 1 should be going to 0. So we factor out the ideal generated by the determinant minus 1, x11, x22 minus x12, x21 minus 1. And that's a ring, obviously, and it turns out that these maps I've defined above, the antipode, the co-unit, and most importantly, the co-multiplication, they all factor through this into this algebra. And what the co-multiplication turns out to be, if you just think about it for a couple of minutes on a bit of scratch paper, you'll see this this definition in terms of maps on G cross G translates to the xij's as just saying delta of xij is the sum of the xil tensor xlj's as L goes from 1 to 2. And so you can see, by the way, that's not in general going to be co-commutative, but we do certainly have a commutative algebra there. The multiplication is just coming from the polynomial multiplication. Good, okay. And just very quickly in passing, finite group, which I mentioned earlier, that's an affine algebraic group. What happens when we play this game with a finite group? Well, basically O of G in this case is just all the set maps from the set G to K. And so just by extending linearly, that's the same as the maps from KG to K. So it's just the dual, the vector space dual of the group algebra. That's all it is. And so it has the same dimension as the group algebra, but it's a commutative algebra. And this is it's important to see this little example, or this little example is actually an infinite family of examples, but it's still very instructive, because one of the things that isn't really going to be obvious at all from what I'm saying today, but is true, is that everything in Hopf algebras is dual somehow, that everything has a dual. And this is kind of a little glimpse of that this Hopf algebra, KG, the vector space dual of it is again a Hopf algebra, and actually carries the same information as KG does, you know, and vice versa. Okie doke. So what did we do there? We looked at some examples of co-commutative Hopf algebras, and we looked at some examples of commutative Hopf algebras. And it turns out in both cases, we've nearly said everything there is to say, at least in characteristic 0. It's more complicated in positive characteristic. We've nearly said everything there is to say about these classes of Hopf algebras. So first of all, for co-commutative, here's the situation. This is a very famous theorem, which these three men somehow or other proved separately, but credit is shared between them, Cartier, Gabriel, and Constant, across the 1960s. So take a co-commutative Hopf K algebra, and we've got this field algebraically closed at characteristic 0. Then H is the smash product of an enveloping algebra of a Lie algebra with a group algebra. Smash product just means that it's, as a vector space, it's a tensor product over the field, but the elements of the group act on the enveloping algebra. So the elements of the group don't commute with the elements of the enveloping algebra in general. It's sometimes called as a skew group algebra, with the coefficient algebra being the enveloping algebra. So the two ingredients that we saw earlier, the enveloping algebras and the group algebras, smashed together give us the whole story for co-commutative Hopf algebras in characteristic 0. And just as we go past, let me just say that the co-product is the same as it was when we just looked at them separately. So for the elements G of the group T, delta just sends such an element G to G tensor G. And for elements X of the Lie algebra, delta sends X to X tensor 1 plus 1 tensor X. And these sorts of elements in Hopf algebras are called group-like and primitive, respectively. I think that terminology comes from Constant, actually, back in the 60s. Commutative then. So this theorem is due to Cartier in the I think really the late 1950s. So take H, a commutative Hopf K algebra, finitely generated as an algebra. And remember, we're algebraically closed and we're characteristic 0 for our field. Then all we get is a coordinate ring of an affine algebraic group. And the content of Cartier's theorem is to say that the Hopf algebra has to be semi-prime. Once you know it's semi-prime, then it's automatically the coordinate ring of an affine algebraic variety, as you know. And then seeing that the Hopf structure gives you a group is not hard. So really what Cartier proved is that the algebra is reduced. No non-zero, no potent elements. So that looks like it might be the whole story, that every Hopf algebra is either commutative or co-commutative, and we understand them all, at least in characteristic 0. So that's not true, as people realized in the 1960s. And the easiest example is due to Sweedler. So it's a tiddly little thing. Let's just think about what it looks like. It's dimension 4 vector space. We can describe it as vector space with basis 4 elements, 1, x, g, and x times g, where the square of g is 1. So g generates a cyclic group of order 2. The square of x is 0, and xg is minus gx. So it's only just non-commutative. And the co-product, G is a group-like element, and X is almost primitive, but not quite. It's what's called skew primitive. So delta of X is X tensor 1 plus G tensor X. So the G in there in the second tensor stops the algebra from being co-commutative. And then epsilon and does what you'd expect it to do, namely it sends X to 0 and G to 1. And there's what the antipode does. And you can play with this and easily check that all the axioms are satisfied. And it's obviously not commutative because of xg being minus gx. And it's obviously not co-commutative because of this skew appearance, the element g in the co-product of x. So this was maybe the easiest, it is the easiest non-commutative, non-co-commutative example. And this was about 1969, Sweedler wrote this down. And I think 2 years later, Taft published a paper where he showed that this is the first, this four-dimensional example is the first in an infinite family. For every positive integer, there's a non-commutative, non-co-commutative Hopf algebra of dimension 2n that looks very much like this four-dimensional one. And these are called the Taft algebras nowadays. Okay, so maybe this is kind of halfway or a little bit past halfway. So I'm going to tell you a little bit of history, but before that, any questions or comments so far? Nope. Okay. So for the history, I should say there's some references at the end of my slides, which, and one of them is a paper by Nicholas Andruszkiewicz and Walter Ferrer Santos, which is a little paper on the archive about history of Hopf algebras. And what I've written on this slide owes a lot to their paper, and their paper has a lot more on the history. So the first appearance of what we nowadays call Hopf algebras was in this 1941 paper by Hopf in Algebraic Topology. Of course, he didn't call them Hopf algebras, and in fact, they didn't have an antipode in Hopf's picture, and they were all co-commutative. They were first called Hopf algebras in French by Borel, still sort of mainly working on algebraic topology then in 1953. The first kind of formal axiomatic definition was by Cartier, 1956, and he was coming, so there's these kind of two strands somehow, the algebraic topology, which connected with Lie theory, that strand on the one hand from Hopf, and the geometry, algebraic geometry side, which came via Cartier, but he was influenced a lot by Dieudonné, another famous French mathematician of the 1950s. So these two strands came together, and people gradually realized in the 1950s and early 60s that the same objects were being studied in these two different fields, and that development grew pace with these people, Hochschild, Kostant, Sweedler. Sweedler was Kostant's PhD student and wrote the first book on the topic in 1969. It's still, it's still in use, still a valuable resource, Sweedler's book. And I mean, maybe for the next, after when Sweedler wrote his book in 69 until, the early 80s, Hopf algebras were quite an obscure corner of algebra. I did my PhD, I finished it in 76, and I'm pretty certain I had no idea what a Hopf algebra was in the 1970s. So they were quite a niche corner of algebra. And then in the early 80s, from working integrable systems and mathematical physics, people discovered huge groups of non-commutative, non-co-commutative Hopf algebras, which were important in these applied areas. And this was brought to the world's attention by Drinfeld's very famous 1986 International Congress address, and quantum groups were launched on the world, and then Hopf algebras became a huge topic, which they continue to be very important till today. So that's very, very rough and probably inaccurate version of the history, but gives you a little bit of the flavor. Now, what about the second part of my title? Why should we care about these gadgets? So there are many reasons. I'm going to focus on two. One is representation theory, and the second is deformations and quantizations, connecting a little bit with this quantum groups that I mentioned earlier. So representations, first of all. So a representation of a Hopf algebra is just a representation of H as an algebra. So as I'm sure you all know, this just means we've got a vector space V and an algebra homomorphism from the algebra H. I'm calling this map rho, from H to the endomorphisms, the K linear endomorphisms of V. And I'm just going to write H times V rather than rho of H times V, just for simplicity. The great thing about Hopf algebras is it lets you multiply representations. And of course, what we mean by multiplication is really tensoring. So the point is that if V and W are two representations of H, then so is the tensor product, V tensor W. And all we do is we use the coproduct to make our Hopf algebra act on V tensor W. So there's the rule there. So H applied to V tensor W, all I do is I hit H with delta, and that gives me sigma H1 tensor H2, and then I let the H1s act on the elements of V and the H2s act on the elements of W. And it turns out this works. It's wonderful. So probably most of you know this already for the special case of H being group algebra. If we've got two representations of a group, V and W, then their tensor product is a representation. And if you remember how that works, it just G applied to V tensor W is just G of V tensor G of W. And remember, delta of G for G, an element of the group, is just G tensor G. So this is just a special case of the general formula up above. So we're thinking for the next couple of slides, starting with that idea of multiplying representations of what is the structure of the set of representations. If we think of it as having some operations on it, like multiplication, well, it looks like a monoid when we've got a Hopf algebra. So a monoid semigroup with a 1. So where's the 1 coming from? Well, here it is on this slide. Every Hopf algebra has a special, an important designated module, which is one-dimensional as a vector space, and it's usually just called the trivial module, and you get it by letting H act via the co-unit. So H of V is just epsilon of H times V. So in the case of a group, then the elements of the group just act as 1, because epsilon of little g is 1, if you remember. So that gives us a one-dimensional module, and this is our identity element if we're thinking about multiplying representations. Because the Hopf algebra axioms, if you look back, you can check this. Let's not do it. Let's just take it on trust. V tensor K just keeps me with V, and K tensor V as well for every representation V. Co-associativity of the coproduct makes sure that our multiplication, our tensoring of representations is as an associative operation. So V tensor W tensor Y is the same as V tensor Y tensor W. So we get a monoid. And this is the beginning of a huge subject that I'm not going to say anything more about really, but it's the study of what's called tensor categories, and has lots of applications to knot theory, integral systems, mathematical physics. Yeah, hugely active current area. And I've put a reference to, there's a book by Hopf and co-authors on tensor categories, which is very good. And I've put the reference to that in the references at the end. And actually, Pavel Hopf has this book freely available on his website, so on his homepage. So I strongly recommend it if you're interested in learning more about tensor categories. What about this monoid being commutative? Well, if H is co-commutative, then V tensor W is going to be isomorphic to W tensor V, because if you think of the flip map from V tensor W to W tensor V that just flips the tensorands around, that's going to be a map of H modules, provided H is co-commutative, provided these delta of H's are symmetric, but it won't be in general. So H isn't, if H is not co-commutative, then in general, you won't get V tensor W being isomorphic to W tensor V, which is actually interesting in itself. But even more interesting is for some H and some categories of H representations, for instance, maybe all the finite dimensional ones or something like that, in the case of quantum groups, then you can find families of H isomorphisms for every pair of representations, C, V, comma, W, I've called them there, that map V tensor W to W tensor V, isomorphisms of H modules, but not just with the flip map. So in particular, it might be that if you apply the map and then it's CWV after it, you don't get the identity. And these sort of things are very, very important in applications to, for instance, to physics, because you can look for maps like this that satisfy some sort of commutativity condition, like, for instance, the braid relations, more or less equivalently, the quantum Yang-Baxter equation, and that gets you into applications to physics. So that's a glimpse, but I won't say any more about that. So other reason why, among several, but here's another one I want to mention, deformation and quantization. And this is somehow something that arose in physics in the 70s, the idea of deformation and quantization, but was realized that these Hopf algebras discovered in integral systems initially in the 1980s were examples of this process. So I'm going to give you one little example to show how that works. Let's just read this first of all. The realization that many classical objects, for instance, enveloping algebras and coordinate rings of affine algebraic groups, hide behind themselves. They hide infinite families. They're just a little visible classical part of infinite families of non-co-commutative Hopf algebras. These non-commutative, non-co-commutative Hopf algebras usually involve parameters, just a variable element of the field or elements of the field, the ground field. And if you take limiting values, so maybe let the parameter go to 0 or maybe to 1, and you get back the classical object, which is the kind of previously the only visible part of this whole universe. So here's one case. If you remember, some slides back, we looked at O of SL2. And O of SL2 was this factor of polynomials in 4 variables by the determinant -1, and was a basic example of a commutative Hopf algebra, the coordinate ring of SL2. So this algebra here, OQSL2, is called the quantized coordinate ring of SL2. So Q here is just a non-zero element of the ground field. And we take the algebra generated by over as a K algebra over K by 4 elements, A, B, C, and D. And the relations are there on the bottom 3 lines of the slide. And if you look at them, don't try to read them all in great detail, but the basic point is obvious. If you look at the first 2 lines of them, so that's the first 6 relations, they all become just rules saying that things commute if you make Q equals 1. So if you put Q equals 1, all the first 6 relations just say that one generator commutes with another generator. And if you take the final relation, you can see that that's just a distortion, a deformation of the determinant being equal to 1. If we think of A as being x11, D as being x22, etc. And so when Q goes to 1, you get back OSL2K. But for every value of Q, this gadget here is a Hopf algebra. And it's the simplest example, as of course you would expect, of an infinite collection. Well, just take any semi-simple group in place of SL2, and you can play the same game, really. And so it's amazing, very, very beautiful, and the beginning of a huge subject. And there's a whole parallel topic on the other side of the duality, as it really is, where instead of taking commutative algebra, O of SL2, I take a co-commutative classical object, enveloping algebra of a semi-simple Lie algebra. And when I do that, I can also deform it like this, and I get what is called quantized enveloping algebras, or quantum groups, as some people call them. So it's a huge subject, which we just note in passing. So what have I got left? I've got about a minute, I think, left before questions. So here's just a glimpse of some current ongoing research. What has happened in the last 30 years in Hopf algebra since the discovery of quantum groups is quite a lot of people around the world are trying to understand the structure of general infinite dimensional and finite dimensional Hopf algebras. Maybe in the case of infinite dimensional ones, impose some finiteness condition, for instance, that they're Noetherian, or something about the growth being not too fast. That involves this idea of Gelfand-Kirillov dimension being finite. So it's a huge topic. One starting point is a theorem back in the 60s by Larson and Sweedler that says finite dimensional Hopf algebras are Frobenius algebras. What is a Frobenius algebra? Well, it's just a finite dimensional algebra with a non-degenerate associative bilinear form from R cross R to K. And the point about such a form, Frobenius discovered that these things existed for group algebras of finite groups. Of course, those are Hopf algebras, as we now know. And so Larson-Sweedler is a big generalization of what Frobenius realized at the beginning of the 20th century. And homologically, consequence is that R is isomorphic to its vector space dual if R is a Frobenius algebra, and so it's a self-injective algebra. It's injective as a module over itself. So maybe that's not really just a theorem about finite dimensional Hopf algebras. And if you look at examples, then you are led, as myself and Ken Gunnar were in the 90s, to ask, does every Noetherian Hopf algebra have finite injective dimension? And we realized at the same time that actually we wanted to be more precise in a way that I'm not going to explain here, but I'll just let you see that we want a special way of saying have finite injective dimension are they all Artin Shelter Gorenstein, which you can Google to find the definition of or ask me later. But it's a more technical version of having finite injective dimension. And this question is open so far, but all known Noetherian Hopf algebras, all the Noetherian Hopf algebras that we have so far discovered are Artin Shelter Gorenstein, and they have very nice properties stemming from that. Poincare duality of the Hochschild cohomology and homology, and their skew-Calabi-Yau if they're finite global dimension, etc., etc. But no time to explain all that, so I'll stop there and just say thanks very much. And can I just say, Angela, quickly that there's a couple of pages of references. I mean, I can show them, yes, but I was hoping they would kind of stay visible for people.